Welcome everyone to these UK quantum fluids webinar. So good morning, afternoon, or evening to all of you, depending on which part of the world you are. My name is Davide Proman. I'm one of the organizer of the quantum fluids UK Quantum Fluids Network, and it's my pleasure today to chair this webinar. So today we're going to have Luis Aldemar Peña Ardila to give a talk on dipolar condensates from binary quantum mixture to polaron physics. Luis studied in Colombia, where he's originally from, then moved to Trento in Italy for his PhD in 2015. And then he did some postdoctoral positions in Germany, Dresden, Hanover, and also Denmark, Aarhus. And then from this year, 2023, he has a position of junior assistant professor in Camerino in Italy. So please, Luis, the stage is all yours.
Okay. First of all, can you hear me?
Yes.
Yes, perfect. So thank you very much, David, and all the people in the UK Fluids Web Seminar Initiative. I think this is a very nice idea, and I'm very happy to be here to talk to you about some stuff that we have done in the last couple of years related with dipolar condensates. So I'm going to talk about dipolar condensates from binary quantum mixtures all the way to the polaron physics limit. So first of all, let me start with a very basic slide, just to get some context about the idea I would like to bring later. So let's start with the paradigmatic state of the matter, right? That we know in the high school, the gas, the liquid, and the solid. So essentially, the difference between this state of the matter is given by the interplay of the most relevant energy scales of the system. In the case of a solid here, we have that the attractive force keeps the particles together tightly, forming, for instance, ordered structures, crystalline structures, or even amorphous structures, in which the potential energy essentially is very large in comparison with the kinetic energy. So we have here a very well separated landscape for energy scales. There is another example that is on the other side of the scale. We have a gas. In the gas, the kinetic energy of the atoms is larger than the attractive force. So the potential energy is almost negligible, and that's why you see that particles bump into each other in random positions with no constrained volume. But there is an intermediate situation in which there is a competition between energy scales. And this is the particular case of a liquid. In particular, van der Waals liquids are formed as an equilibrium between the attractive interatomic force that tries to bring the particles together for large distances, that tries to bring the particles together, right? This is this blue line here, against the repulsive short-range core interaction that essentially arrests the system from any mechanical collapse. So this equilibrium defines what we call the liquids, and liquids are in general self-bound. Now, if we think about quantum liquids, just to mention the series of seminars that having here. So in the case of quantum liquids, the most prominent candidate to see these compact self-bound objects are helium. Helium, we know that has two isotopes, so this is a kind of phase diagram that is pretty much known for people working in helium. Here we have the phase diagram of helium-4, the phase diagram of helium-3. This is the pressure here. In the horizontal axis, we have the temperature. And what you can observe here, and is the only feature I would like to bring for the purposes of my talk, is that at very low pressures and very low temperatures, both helium-3 and helium-4 are superfluid. So under typical experimental conditions, helium-3 can form superfluid droplets below 0.38 Kelvin. That is essentially the temperature below this dashed line here. And these droplets are superfluid. In contrast, for helium-4, helium-4 can also form droplets below a higher temperature of 0.15 Kelvin, depicted by this dashed line here, but these droplets are in a normal state, namely they are not superfluid. But of course, you can combine things together and make things a little bit more interesting. And turns out that droplets can separately form droplets, but when you combine together, they also form this self-found object below a temperature of 0.15 as in the helium-3 case. But of course, here the situation is more interesting because you have another, let's say, degree of freedom is the concentration of helium-3, right? So here, this is the typical phase diagram of helium-3, helium-4, the mixture. Here we have the temperature in the vertical axis, and in the horizontal axis we have the concentration of helium-3. So due to the low solubility of helium-3 into helium-4, and also because these two guys has a different mass, the typical situation that you will find in the experiments is that helium-3 likes to remain in the surface of the helium-4. So it's acting like a coating, as you can see in the picture. However, you can use different, let's say, dopants or impurities to change the situation. And this is the case, for instance, here you have magnesium. So you have these compounds here, these matrix compounds, and you have a situation in which now the impurity that was somehow residing into the surface now gets sucked inside the core of the droplet. And then we have this kind of transition. And of course, this is pretty interesting and appealing for people that want to study superfluidity in the mesoscopic scale, for instance, in this helium-4 matrices. Therefore, the quantum fluids is, of course, a very rich field, combining many body physics, atomic physics, and has a lot of applications in molecular spectroscopy and quantum chemistry. But, of course, there is a but here, is that helium nanodroplets, despite the fact that it's a very fruitful field, and I just wrote a few authors that has done some remarkable contributions on the field, there are some limitations, there are some setbacks in this kind of helium nanodroplets. So the first thing that we can observe is that these systems are not ultra dilute, they are not highly controllable. So typical experiments of helium nanodroplets are quite restricted to certain values. On one hand, we can study properties like superfluidity, immiscibility, we can study impurities, that essentially what I just showed you before in the last slide. But unfortunately, there are some phenomena that are elusive to be addressed, like, for instance, dual superfluidity and the supersolidity that has been has been predicted to occur also in helium. Then, in the community of ultra-cold quantum gases, it was quite excitement when there was the first realization of quantum droplets using, for instance, Bose-Einstein condensates of binary mixtures or dipolar Bose-Einstein condensates. So in this case, the stabilization mechanism is quantum fluctuations. I will be back to that in a second. But what is important here in this slide is that these kind of droplets using ultra-cold quantum gases are ultra dilute and highly controllable. So all you know in this audience that with quantum gases you can control different parameters of the system, and they are ultra dilute, meaning that you can use pretty simple, relatively pretty simple formalisms, like, for instance, the Gross-Pitagevsky equation. That is a situation that is quite different from helium nanodroplets, in which you need to use, for instance, density functional theory or quantum Monte Carlo theories. Okay, in the case of binary droplets that you can form with two Bose-Einstein condensate, you can use dual superfluidity because you have essentially two condensates, but there are some phenomena, like, for instance, immiscibility or supersolidity that cannot be addressed. In the case of supersolidity, this is not possible because here you have essentially short-range interactions, and to study impurities or polaron physics, you need, on top of the two components, another component. So thinking about a three-component Bose-Einstein condensate is always very difficult from an experimental point of view. Now, if we go to the dipolar droplets, here we have a component of dipolar ruled by dipolar interactions. Atoms with large magnetic moment. Here we can study supersolidity. It has been found in this kind of systems in 2019, 3 beautiful experiments predicting the first supersolid behavior using these dipolar droplets. But unfortunately, there are another phenomena that still is out of the chart and is not possible to study, like for instance, immiscibility or polarons, because for that you would need another component. Therefore, you know where I'm coming here. We present a system in which we have the combination of these two guys, binary droplets and dipolar droplets. And in that regard, we might be able to address all these phenomena. So what I'm going to talk today is about quantum droplets in dipolar mixtures. In the first part, how you form these droplets, what is the mechanism behind the formation of these droplets. The second part is related with impurity, nucleation, and supersolidity, essentially how the supersolidity triggers into these systems. And if I have a little bit of time, I would like to talk about a recent work we have been done on impurity physics with dipolar gases. So as you can see, in the first part, I will concentrate mostly in the medium, and in the last part, I will talk about the impurity itself. Okay. The system that, as I anticipate, we will use are dipolar quantum gases. These are essentially atoms with large magnetic dipolar moment. If you want to have a fast pictures about what elements are highly dipolar, are for instance chromium. It's dipolar, very small, but has a dipolar contribution. And also here, these elements in the periodic table, lanthanide atoms, like for instance, dysprosium, erbium. And the interesting thing is that chromium, dysprosium, and erbium, they were Bose-Einstein condensate long time ago. Like in the case of chromium, it was 2005. In the case of dysprosium and erbium, it was in 2011, 2012 by the group of Benjamin Lev and Francesca Ferlaino. Also last year, there was the first Bose-Einstein condensation of europium. You can think about these dipole atoms like small magnets, right? Like you can see here. And then if you apply an external magnetic field, you can write down the interaction between these atoms in this way. So it has a short range pair component. That means that the atoms interact only for very short distances. And it has this this new part that is essentially what features the dipole-dipole interaction that has two elements. First is long range in 3 dimensions, and then it has this term that tells you about the anisotropy of the dipole-dipole interaction. So dipole-dipole interaction is an anisotropy interaction. That means that you have two dipoles sitting side by side, they repel to each other, but if you have tail to tail, they attract to each other. So this is what is telling you this interaction. How do you characterize this interaction? So essentially here you have two numbers. You have this blue, that is the coupling strength associated to the short range interaction. This is also proportional to the S-wave scattering length that can be tuned in experiments. And this magnetic moment is inherent to the dipolar species that you are using. So the parameter that tells me how strong a dipole, how strong a gas is, how dipolar is the gas, is essentially this parameter epsilon dd. That is the ratio between these two guys here. But in the experiment, the interesting thing is that this G, that is proportional to the S-wave scattering length, can be tuned at will, and you can actually change the magnitude of the dipole-dipole interaction with respect to the short-range interaction. Another consequence of dipole-dipole interaction is the excitation spectrum of this dipole-dipole interaction that you can see here. There is this non-monotonous behavior of the excitation spectrum displaying a Maxon-Roton structure. This is quite similar to helium, but of course the physics is completely different, because in helium you are talking about a strongly correlated system. Here you are talking about a weakly interacting gas, at least when you are forming this structure. So when you have, let's say, no dipolar interactions, or when the dipolar interaction is very small, you will have this blue line here that is the typical dispersion relation that you have for weakly interacting Bose gas, in which the for short momentum you have the typical the dispersion relation is proportional to the momentum. The dispersion, the proportionality constant is the speed of sound, and then you recover for high momentum the standard free particle dispersion. But then when you change the scattering length, as I was telling you, you change this epsilon dd parameter. What happens is that this minimum soften, so it's getting closer and closer to zero. So for a K critical and for large dipolar interaction, this minimum here touch the zero, and the system tends towards instability. This is called phononic instability, in which the Fourier transform of the dipole-dipole interaction start having imaginary values, and then the system has the tendency to have a crystallization, because as you can see in this figure, then you have now that most of the average configurations in the between the atoms are tail to tail, right? So you have this attraction, and now if you write down somehow, if you write down the mean field energy for this configuration, you have that the mean field energy should be negative like this, goes like n squared. Sorry, I forgot here. This is the energy, like the density energy in the mean field, depending on short range plus long range. But since you have this tail to tail configuration, that could be negative. And then in order to minimize the energy, you need to have a very large n, right? So the system will try to put all the particles, cluster the particles in such a way that minimize the energy, and that means that the system has a collapse. The system will implode. Actually, there was in 2006, I think, experiments by Tillman found, which they were trying to, they try and they succeed to study this collapse with chromium, and they call these Bossa Nova experiments. And 10 years later, when they explore the same, try to explore the same phenomena with dispersion, they observe that the system actually don't collapse. The system don't collapse and forms these kind of cluster structures here. So it was a big surprise for them why this was happening. And it turns out that the answer is coming from a beyond mean field term that it appears here in the equation of state. So again, if you have your density energy here, right, that depends on the short range interaction and the long range interaction, and this term is negative, the system should collapse, right? But then there is a new term here that is called the beyond mean field contribution, or the Lagrangian contribution, that stabilizes the system against collapse. And this term here depends on the density to the phi half and kicks in for densities on the order of 10 to the 21 atoms per meter cubic. So you can actually now have a compensation between these two terms. That it was is not trivial for a very simple system. Like, for instance, if you have a Bose-Einstein condensate, right, and then you write down the beyond mean field contribution of this equation of state, you have that by definition this contribution is a perturbation. But in this case, is actually a term that can be comparable to this mean field contribution. Therefore, the system is stable and you can form droplets. Particularly here, we have two pictures taken from these beautiful papers realizing these first droplets in dipolar systems. The situation also is similar. If you remember the table I flashed at the beginning, I was showing at the beginning. In this table, I also show the droplets with two-component binary mixtures. So it's essentially the same mechanism, but here, instead of the short range pair and the long range pair interplay, here you have the interplay between the interspecies and interspecies interaction that will give you a stable droplet using the two-component system. Okay, before keep going, I would like to ask if somebody has questions. Otherwise, I can move forward.
Please do continue. Yeah.
Perfect. Okay, now you have these droplets, right? So these objects self-bound. And these are self-bound droplets, as you can see in the title here. That means that you don't need any confinement, so you don't need any trap. There is an equilibrium between two forces, as you can see here, and this is pretty much resembling at what I was telling you at the beginning of the talk, right? But now what happens if you put these droplets into a trap? What happens is that if you start pumping atoms, right, and you have like kind of trap in this direction, what is happening is that the droplet will see this trap and energetically prefers to split into different droplets. And now the very well posed question is, are these droplets talking to each other? In other words, it has these droplets has a phase coherence, and therefore it comes the concept of supersolidity. So supersolidity essentially is paradigmatic state of the matter because combines here the superfluid and the crystalline order. And this is happening because there is the breaking of the phase and translational symmetry. So simultaneously breaking of these two symmetries. And of course, the concept might be more general, but I will restrict only to this concept in order to avoid any discussions with condensed matter people. Okay, so in ultra-cold quantum gases, there has been a lot of realizations of supersolid state using different setups. For instance, Rydberg gases, like coupled BECs, also spin orbit BECs, and very recently excitons. This last one is a theoretical prediction, excitons in bilayer systems, in which they also have a supersolid resembling more the original concept of Chester, but it's a theoretical prediction. But the supersolids I'm going to talk today are associated to the dipolar gases here. Okay, so just to sum up, the recipe for supersolidity in dipole-dipole interactions is essentially an stabilization mechanism. So it's the Ling and Yang that I was telling to you before. Then we need trapping, because the trapping will make more droplets, and also this is related with the fact that you have a strong dipole-dipole interaction that is momentum dependent and will give me this peculiar dispersion relation for the dipole-dipole interaction. And finally, the last ingredient is to make that these droplets to talk to each other, and this is fine-tuning. So again, you can tune the S-way scattering length, and you can have actually go from droplets all the way to the BEC, and there is a small region in which you will find the supersolidity. So as I was anticipating at the beginning of the talk, there were three beautiful experiments in 2019 realizing this state for the first time in dipole-dipole gases. Here we have a phase diagram. This is taken from the paper from the group of Francesca Forlaino. Here you have the number of particles as a function of the S-way scattering length. And as I was telling you before, you have a region in which you have the isolated droplets. So you can see here the typical density profiles in which you have very well separated clusters or droplets. Then the typical BEC on the other side of the phase diagram here. This is the typical BEC that of course has this form because it's trapped. And then there is this small region of between 3, 5, 8 knot in which you have this supersolid state. And then this is the kind of density profile that you get. This density profile you obtain after you Fourier transform your time-of-flight absorption images in the experiment. This is an example for erbium. This is an example for dysprosium. So you see again that the phase diagram is different because of course these two guys has a different magnetic moment, but you will see that here the phase diagram has isolated droplet region, an unmodulated BEC region, and in the middle you will find a super solid. Okay, now let's go down to business. So I promised you binary mixtures dipolar systems, and let's see how the story changed with respect to the first part. So, of course, our motivation came for the very beautiful experiments also by Francesca in Innsbruck, Francesca Fellaino, in which they were able to Bose-Einstein condensate a mixture of dispersion erbium, as you can see here pictorially. And this is our starting point for to study, for instance, droplets and supersolidity in this kind of binary systems. So this is my system. It's a little bit more complicated than the previous one because we have a more additional length scale. So in particular, we have the typical short range physics that is governed by the GAA. So let's say A is blue and B is red. So my short range interaction of component 1, component 2. I have also the inherent nature of the dipole-dipole interaction is encoded here into this GAAD, GBBD, right? My dipolar interaction. And the parameter that I will change in order to access to the different ground state properties is the interspecies GAB. So the component 1, component 2 short range interaction. This is the parameter that I will change. And in the next plots, you will see that as in the horizontal axis. Okay. Now, how I am a theoretician, so if somebody asks me what I'm trying to solve here in order to obtain these ground states, we are solving the extended Gross-Pitagevsky equation that has been featuring in the field for very, very long, except for this part that is relatively new and is bringing all these new physics of droplets and supersolids. So here we have our typical Gross-Pitagevsky equation for component 1, component 2, right? And this kinetic energy, this is the dipole-dipole interaction, this is the short range interaction here. So as essentially this term, mean field term here, all this gray part is the mean field Gross-Pitagevsky, and then extended because you have now this blue term. So our first task is to find this term. So for that, sorry for the technicalities, I just will mention how we get this Lee-Wang correction for the mixture. So just for people that might be interested. So we were heavily inspired by this paper of Hungenhold Pines, in which they found the equation of X-day for a system of hard sphere bosons. And you can find all the typical corrections, the first order correction, second order correction, and boiling down to what you have to do, essentially we need to solve this equation. Here we have the density energy, the Lee-Wang density energy that follows this differential equation, that of course this part is linear and this is nice, but then this part is non-linear and is quite horrible because this depends essentially on the dispersion relation here of the mixture and different parameters like all the length scales I just mentioned before. So in principle, this equation is very difficult to solve, but then we realized that you can see the form of this B lambda here that is coming again from the dispersion relation of the mixture. And then there is a beautiful scaling of the density energy that goes like this. So goes like density to the phi half FP. This is inspired by the scaling that you find in the case of single dipolar case and the binary case with no dipolar interactions. So we have the same scaling, and of course here this function is more complicated but depends only on the polarization. Okay, so here we found this analytical expression for, well, analytical expression for the density energy depending on these parameters, and then we can plug back that into our GP because the chemical potential is essentially the derivative of this energy density with respect to the density, right? And then you plug back into your GP, and then you can obtain the ground state properties of the system. Okay, questions here?
I think that maybe everyone is waiting for the, for the end. Yeah.
Okay, I think I can move on. Yeah. Okay, so we solve our GP equation, right? And the first thing we have access is the phase diagram. Here we have the total atom number, so N1 plus N2. Here we have the interspecies strength. If you remember previously, I was telling you that this is the only parameter that I will change. So everything is fixed, but AAB is my tune parameter that you can tune using Fresnel resonances. Here we have, for the dipolar moments, we have 10 mu B, that is the one for dispersion, and we fix the scattering length for typical parameters like A11, A22, 70, A0. So here we have in the phase diagram for this typical number of particles and this typical interspecies interaction, we have a miscible droplet that looks like this. But this is not a big surprise. What is was the big surprise is actually what is happening here, because if you increase now the interspecies interaction, what is happening is that the droplet that was the one droplet that was inside the other one tries to get expelled out, but you form this kind of molecular structure. So the droplet that was inside expels, get out, right? But then the dipole, since the AAB, that is a repulsive interaction, trying to push away these two droplets apart, is the dipole-dipole interaction that brings the system together. And of course, the system is stable. This physics is completely different to the case of the miscible no-dipolar system, because in the case of no-dipolar interactions, the droplets follows a relation between the polarization and the ratio of the scattering length. So essentially the spin mode is frozen because there is this relation between the polarization and the SY scattering length. In other words, in the no-dipolar case, when you have the droplet, if you don't fulfill this, so if you don't fulfill the equality here, essentially your droplets evaporate. But here we don't have that problem. So the spin mode is free here, and we can have access to, for instance, these new states. Okay, but it still is no. It's not quite trivial to understand why this is happening, right? So our approach is to use an impurity approach in order to understand the different states, the different ground states. In particular, what is happening, why is miscible and why the system is immiscible, and for which parameters that's happening, right? So we use an impurity approach. Essentially, we can write down the mean field potential that the impurity is filling, and this is written like this. So you have the typical mean field energy, this is the dipole-dipole interaction, and this is the beyond mean field contribution, that in terms of polaron energy or solvation energy, this is the mean field energy, and this is the beyond, this is the Froelich terming, and this is the beyond Froelich terming associated to the quantum fluctuations. Now we can plot here this potential or polar energy, as you wish to call it. And here we have 3 different ground states. So let's go little by little. The first one is a miscible one. So using the first part of the phase diagram, so we have here one droplet inside the other droplet. For these typical parameters, this is a miscible, not a big surprise. Then if we increase the AAB, so as I was telling to you before, now you have this repulsion, right? So the impurity is expelled out from this droplet, but is repelled out, and this mean field residual interaction that now is negative, trying to bring this impurity into the surface, right? And this is the situation that you have here. And then when you increase the interaction of the second component, that ABB here, what is happening is that the system will, essentially the impurity will spread into the droplet, because there is no preference of being in the North Pole or on the South Pole. So this is very interesting. So just to mention again, this is the miscible case, and then we have two immiscible cases, the asymmetric one, in which the impurities essentially stays in the border, or an immiscible symmetric, in which essentially spreads. Okay, and then there are different combinations, because of course from the experimental point of view, we fix this, it's easier to fix one parameter, but we can play with different parameters, and you can see a large show of droplets here and very interesting ground states, but I'm not going to enter into detail on that. Now let me talk about the supersolidity in these systems, in these binary systems. So we already see that there's a rich zoo of droplets, in particular immiscible droplets that are micro droplets. So the question of supersolidity here is definitely very interesting. So in comparison to the previous case in which we have self-bound droplets, again, in order to have supersolids, we need a trap system. We have that typical harmonic trap like this, and we start with an unmodulated Bose-Einstein condensate like this. So let's say here that you have a fixed number of particles here. You have you fix your scattering lengths. We have different dipolar moments, and we start with no impurities. So if you are into the unmodulated regime, this is what you observe, right? Because now the system is trapped. What would you expect if you add impurities? If you have no dipole interaction, and let's say that you have like typical rubidium or potassium condensate, and you add impurities, what happens is that this impurity into the mean field is acting as a perturbation, and the Bose-Einstein condensate is essentially unperturbed. But here it was a big surprise that even a small tiny doping of impurities will trigger new states here into the first component and the second component. So in particular, will trigger droplets and eventually super solids. So we essentially switch on the impurity, the component 1, component 2 interaction, and we can see that there is a catalyzation of supersolidity because of the small impurity concentration. So that was a quite surprise for us. In particular, if we now draw all the phase diagram, right? Here we have NB divided by N, where N is N1 plus N2, and here we have the interspecies scattering length. Here we have different ground states in comparison to the single component. So we have the typical unmodulated BEC, like this one, right? And then you have, for instance, ID. So ID in one component, ID in other component. We have supersolidity in one component, but isolated droplets in the second component. Vice versa, if you go to these values here. And more interesting, you might have for a small region, double supersolid. So you have supersolidity in the first component and in the second component, because it's I will explain the mechanism why this is happening. But of course, here the phase diagram is richer. One way to characterize the supersolidity, or in particular the superfluid order into these systems, is using, for instance, the contrast. The contrast is defined by the subtraction of the maximum of the density and minimum of the density divided by the sum of the max and the minimum density, right? That will tell you something about what the relative difference between the densities of the two components. But this is somehow a good criteria. There is a more stringent criteria that is called the superfluid fraction a la Leggett, in which you can actually compute what is called what is the superfluid into this system. So in the first case, you will see that when something has contrast 0, because these two guys are essentially the same, right? So you have a superfluid that has a uniform density. You have that a superfluid has a contrast that is 0, while in the case of the droplets, you have 1, because then you have your droplet that has a maximum density, and then you have a void, so you don't have density. Then you have that this is 0. In the there is this small region in which you have that the contrast is between 0.1 and 0.9, and then this is the case in which we define our supersolid. So here this is for component 1, this is for component 2. But I was telling to you there is a more formal way, that is the superfluid fraction Alalecque, that is essentially following this integral here that is coming from hydrodynamic arguments, and you will see that essentially you have this a relation between the contrast and the superfluid fraction. So in particular, here superfluid fraction is 1 for the unmodulated case, as you might know for the for the normal case, right? But then when you have isolated droplets, there is no connection whatsoever, and therefore you have that the superfluid fraction is 0. And again, in the supersolid, you have a superfluid fraction that is between 0 and 1. Okay, so in order to understand the behavior in a more quantitative way, essentially what we use is a polarization, local polarization approximation, in which we can write down our order parameter in this way, assuming that in the central region, the polarization is essentially constant. So when you have the polarization and the central region is essentially equal to N2 divided by N1, then the ratio between the particles. And this is pretty much satisfied in the central region where the supersolid is forming, where all these density modulations are triggered. So in our system, we can write down sort of single model or scalar model GP equation, in which, of course, we have now a short range coupling strength, effective strength, and a dipolar effective interaction that, as you can see here, will depend now on the interspecies short range scattering length, and the GD also depends here on the interspecies and interspecies dipolar length. So you can define here a typical epsilon DD, and what you will find here is essentially that the mixture. So when you let's take an example for polarization 1. So just to illustrate what's happening here, the mixture is more dipolar than the component 1 here, because this can happen for epsilon, for ABB smaller than 85. So for epsilon, AAB smaller than 85, you have that the effective dipolar interaction of the mixture for polarization 1 is always larger than the one when you have only a single component. So the system is always more dipolar, and then hence you will see a catalyzation of droplets earlier in comparison to the case of no single component. So the nucleation of droplets, of course, in the component 1 will happen for values smaller than 71 here, because now the epsilon DD effective is now 1.38, and this is the case in which you will find nucleation, for instance, in the single component case. And this value here that we found with this single model approximation is actually pretty much matching with the threshold between the unmodulated and the supersolid region here that we found with the GP. So it's a very well approximate analytical description for that. Now the last question is, how can we pinpoint the exact transition? So in order to do that, what you can do is actually you need to find the gap, the Roton gap, that will tell you the information about that. If you remember it, when I was telling you about the dispersion relation of the dipole-dipole interaction, when you touch the zero, essentially you start creating this instability towards crystallization, right? So here, what we did is essentially start with our unmodulated system, right? We've solved this equation that it was taken from this article to find what is the gap in the dispersion relation now that you have a trapped system. And then when this gap is zero, you can pinpoint the instability and the at the center of the gas here. In other words, by knowing this, you will know when this density fluctuations will appear on top of the condensate here, right? So here we have a diagram, NB as a function of AAB, and here we have essentially three set of data. The first one is this blue solid line. This is where the contrast is different to zero. So essentially we have already the supersolid, supersolid. So this region here, right? Here the contrast in component 1 and component 2 definitely is not 0 nor 1. So this is this region here. Then this cyan region is essentially when we start seeing these density modulations. And when we start seeing this density modulation without still seeing a minimum, so the contrast is close to 0. So in the verge of the super unmodulated supersolid transition. And this red curve here is our result here, in which we find the AAB critical, in which you will have that essentially the Roton touch to 0. So as you can see, there is a very nice agreement here. Here there is still is still quite good, because there is just a difference of 1A naught, 2A naught, but perhaps the approximation, like local density approximation here, might be arguable. Okay, and okay, so I think I'm not going to talk about this. There are another kind of supersolids that are immiscible supersolids, and in these immiscible supersolids, you can now play with the spin mode. So essentially the instability of the Roton that I was telling you during all the talk is due to the density mode, to the density sector. Now this one can be tuned, and we can exploit essentially the spin sector. Here the interesting thing is that you don't have droplets, but you have domains, and thanks to that you can create large supersolids, and having large supersolids might be also pretty interesting for the future experiments. And as well, another interesting consequence is that these kind of clusters of domains that you form into these supersolids has a density that is smaller to the one that we had before, and that might be also very convenient from experience, because the time scales for the supersolid will be larger. Okay, and in this last 5 minutes, if I'm allowed, I would like to tell you about what happened from the impurity point of view. So this is the first steps, trying to understand what the impurity makes to the many body environment in a polaronic perspective. So in ultra-cold quantum gases, I was telling you about the formation of this beautiful supersolid state, but in this during the same time, 2015, 2016, there were also beautiful experiments trying to realize what is called post-polaron, so impurities immersed in a quantum gas. And these kind of systems, they look alike very much in the low energy regime. So here you have an impurity. This impurity gets dressed by the Bogoliubov excitations of this gas, forming this called post-polaron. And the interesting thing of this system is, again, that you can control here the interaction, and you can study all the polaron physics. That, of course, is very different to the solid state, but as I was telling you, and in the weak coupling, might share some features. So here, what we study, this is of course the first step. I'm not talking here about supersolids or droplets. We are starting with the unmodulated dipolar BC. We want to try to understand what is the fate of this polaron here. What is the time scales of formation? So essentially, for this work, we were heavily inspired by a beautiful experiment reporting the first observation of polaron formation in quantum gases, and this experiment was done in 2021. This is, of course, for the Bose-polaron. There were also some experiments when you use a Fermi gas and what is called the Fermi polaron, but I'm just focused on the Bose-polaron here. So in these experiments, here we have the phase diagram and the phase diagram of the as a function of the impurity boson coupling strength. In particular, this is the inverse of the impurity Bose coupling strength. And as you can see, there is different phase with different regimes for the dynamics. Here we use what is called a coherent variational ansatz to describe what is called the contrast that is defined by this formula here. So the contrast tells you about, helps you to characterize this phase diagram here, and essentially is telling you what is the overlap between the initial state in which you have an impurity interact and a condensate that they don't talk to each other, and the final state, the final polaronic state in which you have now that impurity is dressed by these excitations. So this overlap is essentially what we compute, what experimentalists compute here, and they were able also to build this phase diagram. But what I want to say is that we can use also this very simple variational ansatz to describe this contrast here. And this is what we have done here in our work. Essentially, now we don't have the situation of a gas with contact interactions, because in that case, you have that impurity has no any preference direction. So essentially, the dynamics is symmetric, somehow call it spherically symmetric. So like if you ask yourself what is the speed of or the velocity of the low energy excitations that takes to dress this impurity, it doesn't matter where it comes from, the excitation, because it's always isotropic, right? But here, the situation in dipolar gases is completely different, because as I show you, you have that the dipole-dipole interaction is anisotropic. So we expect that dynamics plays a very important role here as a function of the anisotropy. In particular, here we consider two cases. So we have this kind of trap. As you can see, this is a cigar-shaped trap in which you have that most of the configurations are side by side, namely that the interaction is mostly repulsive, but also we can squeeze out the trap a little bit. And then we have these configurations in which now you have also large contributions from the tail-to-tail configuration, and then you have also this attractive interaction. So here we compute the contrast, and then now you can see easily that this contrast depends on the form of the trap, as you would expect, and in particular for the short time behavior, so the short time dynamics that in the case of contact interaction is universal. Here we find a very interesting result, and is that this contrast will depend on the characteristics of the trap, as you can see, right? So intuitively, you will expect that the dynamics here is different to the dynamics here, because you have now the contribution of the attractive interactions here is non-negligible in comparison to this case. So of course this term features heavily here. And here this delta is, this kappa here is a function that changes of sign, indicating that now the negative contributions will enter into these short-time dynamics of the polar. Okay, and I think this is all what I want to say. So I want to summarize my conclusions in this way. So for binary dipolar mixtures, for binary dipolar droplets, we have essentially the first self-bound superfluid droplets besides helium and droplets. So I was telling you, to you before, you don't need any trap. You can form these structures that are miscible. That is not a surprise, but the big surprise comes when they are immiscible, in which you have these large molecular droplets. The second part of the talk, I was showing you that even if you have a tiny dipolar second component, you can catalyze droplet nucleation and in this unmodulated quantum gas. That is an effect that you, for instance, you cannot find if you consider short-range interactions. And finally, I didn't talk about this work too much, but this is just to tell you that even at the perspective of the impurity, there is very interesting physics, like for instance, the out of equilibrium polaron formation here, that depends very much on the that depends very much on the trap. I think this is no a big surprise, but what is interesting is that actually you can tune these dynamics essentially by changing the trap, because you can do that in the experiments. And this is my final slide.
I think we really need to wrap up.
Sure.
Yes.
Yeah. This is my final slide. So essentially we have here perspectives for impurity physics, in particular to study the out of equilibrium dynamics into this region. For instance, the IDs, the supersolid, the VEC. Another direction is to study more realistic supersolids in the solid state. For instance, the supersolids proposed by Chester, in which you are talking about single particle localization. And the last one is essentially to go a little bit closer on what people do in helium, like using ions into droplets. So we can use our system to study essentially to see what is the effect of this ion into these droplets. And I think this is all. I want to thank the people I worked in the previous years on these projects. So thank you very much.
Thank you, Luis. Thank you for this really nice overview about your very recent and not so recent work on BEC with dipolar interaction. Any questions? You can either unmute yourself or just type them in the chat, and I'll be happy to read them. Well, maybe. Oh yes, please, somebody.
Thanks for a nice talk. Can you hear me?
Yes, I can.
Very good. I was going to ask, I think somewhere closer to the beginning of the talk, you said that the formation of this density period is dependent on the presence of the trap.
Yes.
Maybe you described this already and I missed it, but so what happens, for example, if you start in a thought experiment expanding the trap? What happens to the period of the modulation?
Okay, yeah, very interesting question. So essentially, what you have here, you need the trap because essentially, let's see this figure that you can see. So let's suppose that you have your initial state is like in this configuration. So it's essentially dominantly repulsive. That means that you have a large confinement in the Y and Z directions, and this is the X direction in which you relax the trap a little bit. But now if you change the trap, namely, now if you start relaxing this, for instance, Z direction here, what is happening is that you will find that these tail-to-tail configurations now will will be dominant, and you will see that now the interaction is negative. And this, if you can see this when you compute the dispersion spectrum. So this is essentially when you are closing this gap, this is the kind of situation that you are seeing, and this is a consequence that the system is trapping. So it's essentially you have the system in 1D, right? So you have these 1D repulsive interactions, so there's no problem with the instability. But now what happens if you start opening the trap, right, in the third direction? Now you will see these head-to-tail configurations that are now important, and this is essentially manifested in the dispersion relation as this Maxon roton. Now, when you start touching to zero, this will happen for a specific momentum, right? So what we call the critical momentum. It turns out the density of, the modulation of this K critical, right? This is essentially is related, the inverse of this momentum is related with the period of the droplets here. So there is a clear relation between this K critical and the period of the droplets, and therefore the periodicity of the modulations.
Thank you.
Thank you. Well, I have a question. So when you're talking about an impurity, which type of impurity have you got in mind? So it's like a third component. It's just a single atom.
Yes, thank you very much for the question. So during the first part of the talk, I was talking about two components, right? And also at some point I say at the introduction that having a 3-component system is a little bit challenging. So in the last part of the talk, actually I was talking about a 2-component system. So it's a different, let's say, work. I'm having here, let me go for, So here I have 2 components, right? It's 2 components. These golden spheres here are dipoles, and here I have also a dipole atom. So it's a 2-component system. But what is interesting about the binary mixture, the interesting thing is that here, these golden spheres, if you tune the interaction and under the typical precise experimental conditions, you can have you can form only droplets here and supersolids, right? So this is even a simpler system, but more, let's say, doable from the experimental point of view. Because with a single component, dipolar gas, you can have a gas, a supersolid, and an isolated droplet, right? And then the second component goes there as a prof, as a quantum prof, so as an impurity. So it's even simple in that case. So you essentially, what I consider here are dipolar atoms, and this is also a dipole atom, but not necessarily, can be no dipolar.
So I guess what I was trying to understand, if this let's say impurity is modeled by more than one atoms of the second species, or it's just, let's say, one single atom?
It's just one single atom.
Just one, okay.
Yes, exactly, yes.
So you don't have a couple, sort of coupled GPE equation. You have a GPE coupled with a single Schrodinger equation or something.
Exactly, exactly, okay. Yes, at the mean field level, yes, exactly. So you have 2 components, and then this is a single atom. But of course, we can recover our system like the binary mixture if now you have more of these atoms, right? If you have more components. Then in that case, you have 2 components, and you can think about polarons until some limit.
Okay, thank you. I think Samuel also has another question.
Yes, I was going to ask another question if you don't mind.
Shoot.
So in this super solid state, or the density modulation, or whatever you would like to call it, so if we take this as a solid, then presumably there might be some phonons of the solid.
Yes.
Is that something that has been observed experimentally, or do you know?
Yes. Unfortunately, I haven't talked about that because I haven't worked about. But then, what the Goldstone theorem says is that you for this kind of systems, for instance, if you have an elongated system like cigar shape as I was showing before, then you have that you might have one mode here in the isolated droplet that is more like a crystalline mode, right? Like resembling the modes that you have in the crystal. In the BC, you have your phonons, just as we know. But here, the Goldstone theorem is telling you that you will have two modes, essentially two branches, where you have hybridized modes. So you don't have a pure crystal mode or a pure sound mode. But then these two modes here, they has been experimentally measured. Maybe I should have a plot here. Let me see. Yeah. Let me see even more clear. Okay, I don't have it here. So this is the two Goldstone modes. Okay, so here you can see my slide. So you have this BEC, the typical sound mode, and then when you cross the supersolid transition, it splits into two. And then when you go re-enter the droplet, you will end up with one. So this has been measured experimentally, yes.
Okay, thank you very much.
Thank you. So maybe I can ask one last very quick question. Sorry. So when you've shown all the pictures of these droplets, both in the miscible or unmiscible regime and everything, so the droplets were never really spherical. They were always very elongated. So this is due to the dipolar interaction with some magnetic or electrical field.
Yes,
so
exactly.
Can you vary the shape and make them less elongated, for example, or?
I don't think so, because essentially the system prefers to keep these dipoles into a tail-to-tail configuration. So energetically, if you have this configuration that is cigar shape, or this one that is elongated, in which the dipoles has this tail-to-tail configuration, of course, energetically, they prefer to have the last one, right? So this is like the most natural configuration. If you try to deform the droplet, then what it happens is that it will increase the energy, will cause energy. For instance, exactly. Like, let's suppose that you have this droplet here, right? And then somehow you want to squeeze it in this direction because you want to do more spherical. What it happens is that the energy of the system will increase, and the nature doesn't like that. Then you have to split into different droplets, but the droplets will form always these filaments.
Okay, thank you. Right. Are there any other questions for Luis? We went very far off our normal times.
Oh, sorry about that. Yeah.
No, it's okay. So I don't see any further questions. So, well, let's just thank Luis again, and for this nice talk.
Thank you very much.
Yeah, I don't remember exactly if there's going to be another talk before Christmas. I can't see anything on our website, so I suppose no, probably next talk is going to then be after Christmas. But if not, we'll send you an email shortly about the next talk before Christmas. All right. So thanks, Luis, again, and see you then probably after Christmas.
Okay.
Bye bye.
Thank you. Bye bye. Cheers. Bye.